Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step aside as we continue our Chapter 4 stuff on circles, or what we're going to do within circles. In this case, we're going to look at inscribed angles and other polygons. That's kind of all I have to say on the matter. Let's just jump kind of into it. If you want to check out the PDF down below, you can download it right in the description section. Check out certain timestamps of what I'm going to do. I'm going to start off with a lecture portion, follow along with whatever it is they have to say, because I have no idea. And then a numbers 1 through 40 set that we have, and let's go check it out. So I'm going to, normally I have intros that are very long. This is one of those like, got hat hair, don't care, got to shoot and scoot kinds of things. Got a long night ahead of me, really. Let's go ahead and see core new vocabulary. We have inscribed angle. They do say intercepted arc. Forever, I've been saying, I don't know if they're going to say intercepted arc or not, and now I'm learning that they do. I've been using this phrase even for central angles, and anytime that an angle's capturing an arc, but here they're finally saying it. Awesome. And subtend, honestly, I forget what this word even means. So, we'll see. I don't even know if that's a noun or a verb. So we'll see what that even means in previous words. Inscribed polygons, circumscribed circle. Awesome. We're going to use inscribed angles, inscribed polygons. Hey, how else are you going to use inscribed angles and other polygons with that? Let's see. Using inscribed angle. So an inscribed angle is an angle whose vertex is on the circle. So you look at this red angle right here. B is that vertex. It is on the circle. That's an inscribed angle. We've been talking about central angles quite a bit, something like this. Let's say that was a D right there. And I'm sure they're going to talk about it. But that's a central angle, vertex on the center, inscribed angle right there. Whose sides contain chords of the circle, so from B to A and from B to C, just like that. An arc that lies between two rays, lines, or segments is called an intercepted arc. So this is their first time really referring to it. I've mentioned it before, but I'd call it the arc that's captured by the angle, and that's what this one has right here. If the end points of a chord or arc lie on the sides of an inscribed angle, then the chord or arc is said to subtend the angle. So it is a verb. Chord AC subtends angle B. Honestly, I'm not even going to remember that word. Subtends angle B. Arc AC subtends angle B. Yeah, I guess it's if you have the intercepted arc, then it's got the thing. Honestly, I don't know how they're going to use that word and how it's going to matter to us. It might. It should. I'm sure I'm going to get it a little more. I'm sorry about one of those things. I'm like, all right, it subtends it. Great. Do I need to use that phrase as much? We'll see. They probably use it in theorems. The theorem, measure of an inscribed angle. All right, let me say this before I start it. This is where you're going to start to get more formulas for your things. Before we've been saying how things are just equal. This is equals that. These are congruent, things like that. You're going to get more formulas now, and a lot of them are really based on, honestly, this one formula we're going to say right here. A lot of things that we do, or similar triangles, something about that. But the measure of an inscribed angle is half the measure of its intercepted arc. So, and I'm sure they're going to bring it up, but I want to do it here just in case to have this visual. We have this angle ADB right here. That has some sort of measure right there. Whatever that is, this arc, it's half the measure of this arc's measure. Remember, arcs are measured in degrees. Let's say this is 100 degrees. Okay, well, this is 50. If this is 100 degrees, then this is 50. Now, the thing that I want to bring up is that, remember, there's a central angle that's formed here. Let's say, clearly that's not 100, but let's say that this was 100 degrees. That's 100 degrees. Central angles have the same measure as their intercepted arc, but inscribed angles have half the measure of said intercepted arc. So that's the big part that we want to say. Probably when we say the whole subtends the angle kind of thing, that this arc is double that of the angle that it's subtending, but the angle is half the measure. The proof involves three cases. Now, there are three different things that we'd want to refer to. There's one where the center is on the circle, the center is inside, and the center is outside. I've done these proofs quite a bit in the past. I remember this one more so than the others. I'm sure when they ask us to do it, or when they show it, it's going to ring an immediate bell with this right here on how it works. Excuse me. So there are three different centers, and there are three different cases for which we need to refer to how we can prove this thing. They don't actually, on number 35. So I'm sure we're going to have to prove all three. I'll be good in picking up whatever it is that they ask me to do. They're pretty nice to show. I think it has to do with using the central angle as well. All right, let's look at some examples. Now, this is where drawings can start to confuse people because you have to use instances of the drawing to see what it is you have. You have to hide other parts of the drawing that aren't relevant to what you're trying to find. Now, they ask you to find the measure of angle T in this first one, and they are referring to this angle right here. Now, the thing that can confuse you is you have this zigzag, but you do not want to see a zigzag of this problem. Just look at this angle RTS right here. The only thing that matters to you is this inscribed angle with this intercepted arc. This thing has 48 degrees of an intercepted arc for this inscribed angle right here, T. T is going to be half of that 48, and that's going to be 24 degrees. That's the only part that matters for us. So that's the 24 degrees that goes right there like that. Now, the measure of arc TQ right here is an intercepted arc for this inscribed angle right here that's 50 degrees. So if this is 50 degrees, half the measure of this, then you get to double the 50 degrees, and then you will get, wait a second, what do they want? Oh, and then you'll get 100 degrees right there. Because arc TQR is also a semicircle, you can see here, in purple, because this is a semicircle, because this is a diameter from T to R. You could also take the measure of QR, which is 80. Excuse me. You could find the measure of QR. Oh, we need to get the measure of QR. Got it. Once we find out this is 100, the measure of QR is 180 minus the 100, and this becomes 80 right there. Sorry, this is one of those things where I'm saying more than I'm actually reading. I'm not comprehending what I'm saying. All right, find the measure of each arc here. Another example. Find the measure of arc RS and angle of STR. What do you notice about angle STR and angle RUS? So let's take a look. So they're going to be talking about the fact that angle STR, look at this one, STR and RUS, they are both inscribed angles, number one, and number two, they both share the same intercepted arc. So look at how these two are both inscribed angles on the circle, and they both share the intercepted arc SR. If they both share the intercepted arc SR, first of all, they ask you to find the measure of arc RS. That'll be double that of either inscribed angle. If we know this is 31, that's 62. Now that this shares that 62, that means you can take half of 62, and this will be 31. So what's the relationship with these two? They're the same. They're the same measure because they're both inscribed angles of the same thing. They're both inscribed angles of the same intercepted arc. Example 2 suggests the inscribed angles of a circle theorem, which sets that two inscribed angles of a circle intercept the same arc, then they are congruent to each other. Angle D congruent to angle C in the case that they both share that right there. And again, you can see this as a different kind of shape. What you want to see is inscribed angle here and inscribed angle here, right? Two different sets. Example, find the measure of angle F. Well, it's going to be 75 degrees, just like this one's 75 degrees because this guy shares the intercepted arc GH, that this guy also has GH. So that measure of angle F is also 75 degrees for that reason. Those would be the quickest kinds of problems that we can do. We don't have to go this full bore like, this is a triangle and blah, 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 and they're vertical angles. We don't have to do all that. It's really nice. Okay, let's move forward. Let's look at inscribed polygons. Recall a polygon is an inscribed polygon when all its vertices lie in a circle. So this pentagon is inscribed right here for an example, as all the points lie there. Do all polygons do that? No. Triangles always do. Other shapes, or always can. Other shapes have to be unique and specific. Inscribed right triangle theorem. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. I'm sure they're going to bring some of the stuff up with that and why this is true. It's interesting how they say that. I would have worked the converse. Conversely, if one side of an inscribed triangle is the diameter, then the triangle is a right triangle. Now, the reason for this, the converse is the way I'd always state it, and it makes a lot more sense for me to state. If this diameter, if you have a chord of this diameter right here, then this inscribed angle has an intercepted arc that's 180 degrees. It's a semicircle. Therefore, half of the 180 is 90. Boom, like that, right? Inscribed angle is half the measure of its intercepted arc. Half the measure of that one. And that's the one that I always tend to bring up when we talk about that. So I'm going to always draw a right angle anytime that we see those ones. So I work off the converse much more often. I never really think about saying it the other way, which is interesting. And it's interesting that that's the converse. Let's look at an inscribed quadrilateral and see if we can notice the same bit with this. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So opposite angles, let's say we're talking about this E and this G. Now, we never mentioned that they're 90 degrees, but here's the thing about this. Take a look at, let's do different colors. Take a look at this angle E, this inscribed angle, if you will, and its intercepted arc, this FGD. I don't care if it's minor or major. I'm just going to call it FGD right there. Now take a look at G's intercepted arc right here. What do you notice about the sum? This is probably the proof, but what do you notice about the sum of this arc plus the sum of this arc? It's the entire circle, which is 360. Well, if each inscribed angle's intercepted arc adds to 360, then half of that is these two angles, which will then add to 180, which is cool. And that's going to be true for all of those angles in an inscribed quadrilateral. That is the proof, saying it in some way. They're going to have us do it, sounds like, later. And it looks like I did this proof as well, at least the converse. So that's cool. Okay, find the value of each variable, this 2x. As you can see, we have a diameter. Let me move this. As you can see, we have a diameter from of AB. There we have an inscribed angle from that. This will be 90 degrees. So if 2x is 90 degrees, then x will be 45. Then we have an inscribed quadrilateral here. We're trying to find z and y. No, they're not equal to their opposite angles, but they're supplementary with their opposite angles. So z plus 80 is 180. So z will be 100 degrees. Y plus 120 is 180. So y will be 60 degrees. And they show those right here. Or 160. Okay. Oh, I was hoping that was it. All right, using a circumscribed circle. What? Oh, a circumscribed circle. Your camera has a 90-degree field of vision. That's shown right there. So the camera's shooting out, and this is what you can see from it. And you want to photograph the front of a statue, like the Statue of Liberty. You stand at a location in which the front of the statue is all that appears in your camera's field of vision, as shown right at the ends, You want to change your location. Where else can you stand so that the front of the statue is all that appears in your camera's field of vision? So what you want to do here, like just getting the idea, and I'm going to scroll down to it right now, is this can represent the inscribed angle of a circle. If you make sure that you have points that are on that circle that go all the way there, the 90 degrees, first of all, is a nice inscribed angle for which a circle that has a diameter, the width of, say, the Statue of Liberty in this case. And that's what they're going to say right here. They're going to say, make sure that the hypotenuse of a right triangle in this case represents the field of vision of the statue. So you can be anywhere. You can be anywhere on this circle and have that view, maybe not dead on with full on symmetry and stuff. You can be at an angle and, an off angle here. You'll still get the whole field of view with that anywhere on that circle that's made with the diameter whose measure is the same as the width of the statue. I can even be all the way on the side right there, and I can get field of view, boom, boom, and that's still 90 degrees. Which is cool about these things. I like to really show those things with the tools literally the tools that I have right now with this computer program stuff. I can do all that. Okay, that's some monitoring progress. So because it's not ones that are listed, we're going to do our own, of course. Now we're at our own set, which is good. Let's go ahead and look at numbers 1 and 2, vocabulary and core concept check. Number 1, vocabulary. An arc that lies between two lines, rays, or segments is called an intercepted arc. Now, once again, this is a phrase that I've been using for a while, so I apologize if I used it prematurely. Acre. I did not use it prematurely, though. Any of the ones that we stated before could have been treated as intercepted arcs, including with central angles, and they did not bring that up. They'll bring it up, I guess, in their proof that we have to do later. Number 2, different words, same question. Which is different? Find both answers. The measure of angle ABC, I'll put a letter A there and look at what we're talking about. Now, ABC is going to be a 90-degree angle. I'm going to bring that up right now because it's the inscribed angle of a triangle whose longest side there is the diameter. When you have the diameter right here, those endpoints have an inscribed angle of 90 degrees. So that's going to be 90. I'm just going to write that down and see what we're talking about. Measure of angle AGC. Where's G? There it is. AGC. Well, I know that's not 90 degrees. It's also not an inscribed angle. Right now, I'm going to treat it as the different one until I see something different about it. Measure angle AEC. Yeah. So AEC is also going to be 90 degrees. Once again, inscribed angle, whose endpoints are on the diameter of the circle. And ADC also does the same thing. So these will be A's because they will make 90-degree angle measures right here. They are inscribed angles as well. AGC will be different. AGC's measure, by the way, if these are 25 truly there and there, 25 plus 25 is 50. 180 minus 50, because that's a triangle, is 130, and that's that measure. So that's different. These are 90, and this is 130. Okay, so I'm going to hit that 3 through 8 coming up next. It's going to go all the way 3 through 40. Go ahead and get your stuff printed out or ready to go, and I'm going to get started in 3, 2, 1, and go. Let's go ahead and start taking a look at numbers 3 through 8 where we find the indicated measure, and I'll leave the drawings over there on that side as we go mosey on forward. I might mark some things here and there if you caught the lecture section of what I just talked about. Measure of angle A, this is an inscribed angle whose intercepted arc is BC. So the measure of the angle is going to be half that of the measure of its intercepted arc BC, which is half of 84, which is 42 degrees. I'm unlikely to show this part quite often here. I just wanted to get the first little nugget of what that thing is. Number 4, measure of angle G, also an inscribed angle. However, this time, and they're going straight into it, measure of angle G, it's half the measure of this intercepted arc. So I want to find out what that intercepted arc measure is right there. So here's the thing. We got to do half the measure of 360 minus the sum of 70 and 120. So here's the idea on this one. Oh, let me do this actually. Let me put this down below. I'll do once again 1/2 the measure of arc FD. I believe it would be a minor arc. Yeah, just barely. So I need to find the measure of this arc. Whoopsie. And this arc will be 360 minus 70 and 120, right? Here's 70, here's 120, here's everything that's left of it. And that's why we're doing that specifically there. So that'll be half of 360 minus 190, which is half of 170, which is 85 degrees. Okay, let's do number 5. Measure of angle N, that tiny one. And, you know, I like to assume that these things are pretty drawn to scale. So if I get a really tiny answer, then I feel like I did something right. So measure of angle N, this little guy is going to be half the measure of this intersected arc LM. And LM is supplementary to the arc NM because they form to make a semicircle together. So the measure of angle N is half the measure of arc LM, which is half of 180 minus 160. This problem seems technically easier than the one before it. So 1/2 times 120, or half of 120, which is 10 degrees. I expected a small answer. I got a small answer. I feel pretty good about things. Number 6, the measure of arc RS. This one, and it looks like all the way through number 8, goes the other way. Now this time we have the inscribed angle measure. So for me to do this just once, the measure of angle Q is half that of the measure of arc RS, right? So RS, whatever this is going to be half that. So let's say it the other way now. If I double the measure of angle Q, so multiply both sides by 2, right? Times 2 times 2. The 2's cancel here. And if I double the measure of angle Q, I will get the measure of arc RS. And that's how I'm going to say that kind of here on out. The intercepted arc is double the measure of the inscribed angle. So we're going to double 67 degrees. And we get 134 degrees. And that's going to be true for these other two, assuming it's as simple as that. Probably not always, but let's look at number 7. Measure of arc VU. Measure of arc, whoa, not a segment. Arc VU should be, oh, here's VU, by the way. Boom. There's measure of arc VU. Now, I think sometimes using this circle will be significantly easier than all the writing that I'm doing. Let me do this just for one of them. Otherwise, I'm going to go like 180 minus the double of this and that. I think if you see this thing, you're going to kind of feel it out a little bit better. So on this one here, and then I might go back to them afterward, but in case you're confused on what I'm talking about, I have an inscribed angle here of 30 degrees. That means this guy's going to be double that. This will be 60 degrees like that. Now we're looking for the measure of arc VU, which is right here. This is the rest of what makes this semicircle. if this is 60 degrees, this is 120 degrees. And like that would be your answer, right? So 180 minus twice the measure, like, you know what I mean? The measure of arc VT, but the measure of arc VT is twice the measure of the 30, which is 60. So measure of arc VU is 180 minus 60, which is 120. So yeah, a lot that I could say there to kind of make it happen, and that's just kind of our navigation of it. How you choose to do the work's up to you. Generally, if you have the circle there, like this was on a test or something like that, just kind of write numbers there that would work with calculations. Lastly, the measure of arc WX. Let's see if I can kind of just do it on the side here in the same way that I did before. If I can figure out doubling 75 gets me 150 up here, now I can go to work on this arc afterward. This is everything that's not the 150 and the 110 out of 360. So 360 minus the sum of 150 plus 110, or 360 minus 260, which is 100 degrees. And that's the measure of arc WX. So that's what's going on in those ones, whether we take double or half of it. Unlike central angles where they are equal to them, those are exactly half, like I said. And I think at one of these problems, we're going to do proofs of them in a bit. All right, numbers 9 and 10. Name two pairs of congruent angles. Well, there are multiple sets that we can do. So what you're probably looking at is kind of like an hourglass looking figure, but that's not what we care about here. What we actually care about is any set like this inscribed angle here that has this intercepted arc AB. But what other angle has an intercepted arc of AB? Take a look at what's in green that shares A and B and has an inscribed angle on D. That one also does. If they share the same intercepted arc, then they are the same inscribed angle. So number 9, here's an example. Two congruent angles. We can say angle BCA and angle BDA. They are congruent to each other. They'd probably say ACB and ADB, but that's okay. That's one set. Or let's go the other way. And let's look at these two inscribed angles, CBD with this intercepted arc of CD. And let's look at this one over here as an intercepted arc of CD as well. Boom, like that. They share that intercepted arc, so they are also congruent to each other. Let me switch my pen. So this is angles CBD, CBD congruent to angle CAD. Like that. So those are two different sets there. Let me take care of some sniffles for a second. I had a lot of sneezing earlier outside. Okay, let's jump to number 10. Two pairs. Oh, they did say two pairs. I thought they said name a pair. So I actually did more. I actually did exactly as much as I was supposed to do. I didn't do any more. Okay, so this one I'm going to go WXZ, having that intercepted arc, and so does WYZ. So that's one set. Let's do angle WXZ and angle congruent to angle WYZ. And then the other set here, we can go this way, the opposite way here. This guy has this intercepted arc of XY, and then this guy also has this intercepted arc of XY. As long as X and Y are the endpoints of the angle, you know what I mean, the chords, I should say, that make the intercepted arc, then just find the inscribed angle that goes there, and it's like this. So angle XWY congruent to angle XZY. Or that one. So one or the other. I'm sure we're going to have some questions with these ones as well coming up, but just kind of get used to that hourglass looking thing representing what it is. And this problem kind of helps you with it this time. When they show the one that's in red, I think they're going to say find the measure of the arc in red. Oh, of the red arc or angle. So yeah, so they can totally show you the separation this time. This inscribed angle with that intercepted arc, this inscribed angle with that intercepted arc. They want to find the measure of angle EHF. EHF, and that will be equal to the measure of angle EGF because they are both inscribed angles of the same intercepted arc. This is also 51 degrees. Number 12. Number 12 has two different inscribed angles with the same intercepted arc right there. Now, these, you have to be careful. This 45 degrees, honestly, is just throwing you off. It doesn't mean anything to us. That's an inscribed angle for this intercepted arc, which means nothing for me. I want to know this intercepted arc for that inscribed angle right there. So we want to know the measure of arc PS. Measure of arc PS is going to be double that of the 40 degrees, which is 80 degrees. The other angle means nothing to me. It doesn't need to be congruent, nothing like that. There are alternate interior angles, but if the lines aren't parallel, then it doesn't mean anything at all. We're good. All right, numbers 13 to 16, we're going to find the value of each variable. This is for inscribed polygons. Inscribed polygons, in this case, I see inscribed quadrilaterals going on, and inscribed quadrilateral going on in number 13. And what the lecture portion pointed out, and kind of what I proved, I think we have to prove it together officially later, is that opposite angles of an inscribed quadrilateral, they're not congruent, but they are supplementary. They add to 180 degrees. So what I marked in green, the x and the 180, they are opposite each other, x and 80. They're opposite each other, but they will add to 180 degrees. They will be supplementary. So x will be 100. And I'm not putting degrees because it shows the degrees there on the x portion anyway, so we're good. Let's go ahead and get y. Y with the 95 also supplementary. So we should be able to say that y plus 95 equals 180. Subtract 95 over, you get y equals 85, like that. All right, number 14, more of the same, an inscribed quadrilateral. Look for opposite angles in this case. So for number 14, we have m plus 60 equaling 180, so m would be 120. And then we have 2k plus the 60 that's opposite the 2k, also equaling 180, so 2k equaling 120. Divide by 2k would equal 60 in that case. So very quick questions based on understanding that setup of what happens. Again, we're going to hit the proof later, but I did talk about the reason why that is. They're inscribed angles of parts that make the complete circle. Another inscribed quadrilateral, but they have a little more of a diagram and messy stuff going on. Let's see what they're talking about. Number 15. First thing I want to look to do, I don't care if it's relevant immediately or not, but I see 3 out of 4 arcs completing this circle here. 54, 130, and 110. I want to know what this JK is. I really feel like that's relevant to what I want to see with inscribed angles and such. So let's tackle what that is first. Let's figure out measure of arc JK. And this is one of those things that you could probably just write on the circle and you're good. I will after I do the work. So 360 minus the sum of 54, 130, and 110. And I'm sure there are faster ways for me to do what I got to do, but I just see this calling to me. 240, 294, don't need parentheses, sorry about that. This will be 66 degrees. So this is 66 degrees here. And the reason I kind of wanted that is because I was looking at this being a portion of, say, this measure of angle KLM right there. Boom. Because there's the intercepted arc for it. 3A will be half of that. So let's jump into that one. Let's do measure of angle KLM. Let's just write 3A. The 3A is going to be half of the measure of its intercepted arc, which is the sum of the 54 and the 66. So let's keep the 3A here. You know, I could double things right now, but I'm just going to leave it. 54 plus 66 is 120. So half of 120, 3A will be 60 degrees, so A will be 20 degrees, or 20, because the degrees are already represented on the problem. And that's where that one comes in. See, this isn't so much on inscribed quadrilaterals that I feel like I'm dealing with here. I could have, probably in other ways, but I'm good with representing this the way that I see it. And now this 4B is an inscribed angle for this intercepted arc that's 66 plus 110. So it looks like this is good that I use this version. So 4B is half of that of 66 plus 110, which is half of 176. 170, I think it's 88. And divide that by 4, you get 22. So we get A is 20, B is 22. Once we found out that one arc and use the inscribed angle portion of that. I'll keep that there. All right, let me pause for 1 second, get some more water. All right, so far we're flying through a little bit, which is pretty good. Let's jump to number 16. On number 16, we have an inscribed triangle, but this inscribed triangle is very unique in that it has, and sometimes I often don't actually see these as triangles, but this time I'm going to. We have the diameter right here, that chord or what have you, be the diameter. So one of the immediate things that calls attention to me that we've spoke on in the lecture portion is this inscribed angle. See, this inscribed angle has a semicircle as its intercepted arc. Therefore, the inscribed angle here is 90 degrees. That 3x is 90. If I want to solve for x, I can do it right now without any other sort of jump. So 3x equals 90 and x equals 30. That's the straight up bit right there. And I could substitute that in, what have you. The point is that's going to be 90 degrees. So this is a right triangle. I mean, that's part of the inscribed triangle stuff. As long as the diameter is right there, then it's going to be a right triangle. Now, the other two angles in any right triangle that we're referring to are going to be complementary. The 34 degrees right here and the 2y degrees right there. Not congruent, complementary. They add to 90 degrees together. So 2y plus 34 equals 90 in this case, because the third angle is 90. They would add to 180. I can subtract 34 from both sides like that and get 56. Divide by 2, I get 28. Like so. And I think that's the right math on that. So that is the x and y number 16. Okay, number 17, I don't know if 18 also is error analysis, but number 17 is, let's describe and correct the error in finding measure of arc BC. Now, they said measure of arc BC was 53 degrees. They're incorrect on that. That would be true if we had a central angle whose intercepted arc was 53 degrees, boom. Or the central angle was 53, I should say. Its intercepted arc would also be 53, like so. That's not what this is. Instead, we have to double that one to get it. So their mistake was assuming they're the same. They showed the inscribed angle has an equal measure to its intercepted arc. I was really worried that the book wasn't going to use the phrase intercepted arc. I thought that I even went through it and said they probably don't. Whereas instead it should be half its measure. So the intercepted arc is double the measure. So the inscribed angle is half the measure of the intercepted arc. The intercepted arc is double the measure. Is double the measure of said inscribed angle. Now, once again, there is an equal bit of intercepted arc, but not with the inscribed angle, but the central angle. It looks like they haven't really referred to central angles here because that was from a previous section, although they could bring it up. So what is the measure of arc BC? Let's correct it. We should be doing double 53. That's 106 degrees. So that would be the answer to 17. Kind of things we've already done, but we had to actually state their issue. All right, number 18. Word problem. A carpenter's square is an L-shaped tool used to draw right angles. You need to cut a circular piece of wood into two semicircles. How can you use the carpenter's square to draw a diameter on the circular piece of wood? So all you have to do is this. You have to take the tool, and I can't really move the tool, so let me find a way of like making my own right angle thing like this and show you. You have to take that tool and just lie the angle somewhere on the circle. As long as this right angle goes somewhere on the circle, look to where the end points of this thing go and connect them with the segment. That'll make a diameter, because an inscribed angle with a measure of 90 degrees, like that, its intercepted arc will be double 90, which is 180. Therefore, these two parts will work. So all you have to do is place the right angle on the circle. Place the right angle somewhere on the circle. Anywhere on the circle. And use its endpoints. Its endpoints intersect with the circle. To draw a chord. That will represent, they didn't say explain why, I did, but that will represent the diameter. A diameter of the circular piece of wood. Yeah, that's the theorem version of it. You know, like if you heard me in the lecture portion, I stated I'm more comfortable talking about the converse of it. That's how I always bring it up. This is technically the original theorem in play. And I've never really mentioned it that way. We kind of always talk about the converse whenever we can. All right, let's do some mathematical connections, see what they're asking about here. In exercises 19 to 21, we are going to find the values of x and y, then find the measures of the interior angles of the polygon. So once we solve them, we're going to go there. So, okay. I don't know if this, so this looks like a system of equations to me, the way that it's brought up. We did mention in inscribed quadrilaterals, opposite angles are supplementary. So we can do this 3x plus 21y, for example. Look how those are opposite each other. These will add to 180. But in that scenario, you'll notice that there's both x and y in it, so I can't solve for just one there. What I could do, and I kind of want to do, I'm going to divide everything by 3 here just to make it smaller. I feel like that's going to help me a little bit, where I get x plus 7y equals 60. Just smaller values. I don't really need the 180 in and of itself. I just wanted something there. Now, the other portion of this equation, the system, is I can add the 2x and the 26y. Those are also opposite each other, and they will also add to 180. But if I divide everything by 2 here, because I can, and I just like to make things smaller when I can when it comes to these, I got x plus 13y equals 90. So I have a system of equations with these two involved, and if you've done anything on systems of equations before, you can solve using several different methods. I'm not going to sit around teaching what I'm going to talk about here, but I could use like the elimination method. Let me do it the other way. I could use like the elimination method by subtracting x's. I could get both x's by themselves, say x equals, and set those equal to each other. Bottom line is it's a system of equations for which you can solve this thing. So normally I don't like to play the subtraction game, but since they're all positive, I think it's pretty easy to do. X minus x is 0, 13y minus 7y is 6y, 90 minus 60 is 30, and I can solve for y, and I get y equals 5. So that's one version. Like I said, if you want to get the x's by themselves and set those expressions equal to each other, then you can also get y equals 5 there. Now, I want to solve for x, and this will help by substituting into either expression. So let's go ahead and take these both together, substitute y equals 5 there, and get x plus 7 times 5 equals 60. You can use any original equation that you want for this. And x plus 35 is 60, so it looks like x will be 25. And I didn't double check any of this, but it's looking pretty good to me. They did say find the measures of the interior angles of the polygon afterward. So I think in doing so here, we will confirm that everything works the way that we intended it to. So I'm just going to call them like measure of angle A, measure of angle D and stuff. I don't think we'll be confused on what those are. So measure of angle A, and these weren't in the notes, by the way. Measure of angle A is going to be 26 times y, 26 times 5. That's 130 degrees. So there are a couple ways we can confirm we did this correctly. The first way is by seeing that all these add to 360, ultimately. The other way is seeing that opposite angles were indeed supplementary. That's the probably better version of it. Because if they're both supplementary, then that means that they did add to 360 as a whole. 2 sets of 180. 3 times 25 is 75 degrees for B. Measure of angle C is going to be 2 times 25, which is 50 degrees. Now, 50 plus the 130 is indeed 180. So that's one of the supplementary sets right there. And the measure of angle D is going to be 21 times the y value of 5, which is 105 degrees. And 105 plus 75 is also 180. So it seems like those are the right answers for that system. So there was a little bit to do on the problem, and it comes with solving systems to make it happen. Looks like we got to do it again for number 20 and probably number 21. So number 20, we have, once again, opposite angles that are going to be supplementary. So A and C are opposite each other. B and D are opposite each other. They will separately add to 180. So let's take a look there. Let's do the C plus A. 14x plus 9y equals 180. And we have the other one that's 4x plus 24y equals 180. This one can't really simplify, so I'm just going to rewrite what's there. The other one can. We can divide everything by 4, actually. So I'm going to go ahead and do that, divided by 4, and we'll get x, 1x, plus 6y equals, not 180, 45? I think it's 180 divided by 4 like that. Let's use a different method this time. I used elimination method last time because the x's were the same. They kind of subtracted out. This time that doesn't really happen. This time let's do a substitution method version. So actually let me not even rewrite that other one. It's not really needed at this point. I divided everything here by 4 for the other one though, right there. And what I'm going to do is get x by itself, if you don't mind. Let me kind of change this. Divided by 4. Okay, let's subtract 6y from both sides. I'm going to get x equals 45 minus 6y. I'm going to take this expression, and I'm going to substitute it in for x in the other original equation right there. This will give me an equation with all y's. This is solving systems of equations. So 14 times 45 minus 6y plus 9y equals 180. And we'll use this one to solve for y. 14 times 45. I should make this easier for myself. 45, 180. 630, I think, minus, I should know 14 times 6. 84. 84y plus 9y equals 180. This is going to be negative 75y. And this is going to be negative, now they're both negative, negative 450. And divide by negative 75. Let's just hope it's clean. Let me just use the calculator. I don't know why I can't do this. Let's hope it's clean and that I didn't mess up any numbers like that other calculation. 450 divided by 75. 6. Y equals 6. Okay. Let me fix a sniffle. Hold on. I said let me fix a sniffle. Let me address a sniffle. Okay. So y equals 6. Now let's solve for x. And this is a pretty nice place that we can do here since we use substitution. I can now do x equals 45 minus 6 times 6. Y is 6 there. So x is going to equal 45 minus 36, or 9. So y is 6, x is 9. They do want us to find the measure of the angles themselves, so we get to play substitution here after. Measure of angle A is 9 times y. 9 times 6 is 54 degrees. Measure of angle B is going to be 4 times x, 4 times 9, which is 36 degrees. I just kind of look at the angles and see if they look like they're drawn to that scale. So far, so good, I believe. Measure of angles, this is where we got to get bigger ones, though. So 14 times that x, 9, is 126. And then measure of angle D is 24 times 6, which is 144 degrees. Now let's see if that worked out. 144 plus 36 is 180. Those are opposite angles. And opposite angles here, 54 plus 126 is also 180. So those numbers look good. All right, the last one, number 21 here. Not the last problem. In fact, we're only halfway through. So we're through the quicker part. Number 21, I have triangle stuff right here, right? And it's actually, it's also an isosceles triangle because these intercepted arcs, well, okay, so what I'm going to bring up is here is an inscribed angle for this intercepted arc that is 6y. We also have another one, an inscribed angle right here, which also has an intercepted arc of 6y. I'm curious if that's kind of the way that they want us to bring about that part. I'm thinking of the best setup. One portion of the setup I can say for sure is if I 2x is half the measure of its intercepted arc 6y. That means 2x equals 3y. That's one portion of this that we can say is a for sure. Now, the other portion is this 4x being half the measure of this intercepted arc here. Excuse me. It is the intercepted arc, which is double the measure of this inscribed angle. Now, I'm trying to think how they want to best do that. We have some options. We can either, I think this is the way you can probably solve for x. This can be represented as, remember, if this is 2x, this will also have to be 2x. It's just the isosceles triangle nature. And this could be 180 minus the 2x, the 4x? Like that? Yeah, we can just use that. If that's 180 minus 4x, we can say, and this one doesn't really need a system. It is a system, but we don't have to use both parts to interact. 180 minus 4x is half the measure of its intercepted arc being 4x. So 180 minus 4x, again, a triangle's angles add to 180, so take away the two x's that we have there from there, and this is what we have. Add 4x to both sides, we get 6x, and divide both sides by 6, you get x equals 30. So if x equals 30, we know that 2x equals 3y. That therefore means 2 times 30 is 3y. So 3y is 60, and y equals 20, therefore. So we got 30 and 20. Now they did state, find the measures of the interior angles of the polygon. So the polygon's angles, we have both things that are 2x's there. I'll just start with those. So measure of angle A and measure of angle C will have the same angle measure. This will be 2 times 30, which is 60. Whoops, 60. And you have a bunch of degrees, and you have a bunch of different ways you can find measure of angle B. We already have the expression as well, the 180 minus 4x, so I can work off that one. So 180 minus 4 times 30, 180 minus 120, which is also 60 degrees. So everything is 60 degrees. It's an equilateral triangle. It looks equilateral, if that matters to us. We could also see that these would be the same measure. 6 times, what was y? 20 is 120, and 120, and 4 times 30 is 120. So same intercepted arc measures, same interior angle measures, all good. All right, number 22, making an argument. Your friend claims that all these angles here are congruent. That's PTQ, PSQ, and PRQ. Is he correct? Excuse me, is my friend correct? Explain your reasoning. Yes, my friend is correct. This is because they are all inscribed angles of sharing the same intercepted arc. My friend is correct because they mentioned 3 inscribed angles which all share the same intercepted arc. There's the theorem. I forget what the name is, and I'm sure an actual official answer key would say yes by the blah, blah, blah theorem. Intercepted arc congruence theorem, or common intercepted arc theorem, or something. All right, numbers 23 to 28. In these, determine whether a quadrilateral of the given type can always be inscribed inside a circle. Well, notice that the way that we stated whether quadrilaterals are inscribed inside a circle, they need, or when they are inscribed inside a circle, their opposite angles are supplementary. We have to ask ourselves is, are all squares opposite angles always supplementary? Are all rectangles things always supplementary, stuff like that? So what I'm going to state, well, I'll state it one at a time. But for the square, yes. A square's opposite angles are always supplementary because they are always right angles. Right angles always supplementary. They always add to 180. This is also true, number 24, for a rectangle. I could literally copy paste, and I think I will. Copy paste everything here, understanding that, oh, even the 23 portion of it. No, 24 portion of it. Understanding that a rectangle always has right angle and 90-degree angles as well. So rectangle, also a yes, for the exact same reason. Number 25 is parallelogram. Parallelograms' opposite angles are always congruent, but they're not always 90, so not always supplementary. Parallelogram is no. In fact, a parallelogram is only inscribed inside of a circle when it's a rectangle. So no, opposite angles congruent, not supplementary. Only in the case of rectangles, and they said in always cases. This is not one of those always cases. 26 is a kite. I don't think that's true of kites, right? No. So kite, no. Just, I mean, I don't know what to explain there. Just not always supplementary, right? When you have a kite, you can have it kind of, look like that if you want to the extent that, sure, this could be 60 degrees and this could be 120, and then these are both whatever. These opposite angles would have to be right angles, so I can say that, because those opposite angles are congruent only when one pair is 90 degrees. Here's the thing, the opposite, there's one pair of opposite angles of a kite that's always congruent, so this one, when that pair is 90 degrees, then the other pair, no, actually, yeah, so that's the only case, and then, yeah, no other case. 27, a rhombus. Rhombus is the same as square when it comes to, or it's the same as parallelogram for answer, but it's the same as only when a rhombus is a square is it kind of allowed. So rhombus is a no. No, for the same reason, opposite angles congruent, not supplementary like a parallelogram. And then we have an isosceles trapezoid. That should work. So hold on. Isotrapezoid. I believe that's a yes. Now let me mention why. Let me show you why. And not just a trapezoid, an isosceles trapezoid. In an isosceles, or in any trapezoid, base angles or angles of different bases, I forget what they call them, they are always supplementary. This x plus y equals 180, period, for any trapezoid. Doesn't matter isosceles or not. But in an isosceles trapezoid, these same base angles are congruent to each other. These same base angles are congruent to each other. So this x plus y is still 180. My drawing is going to be the reasoning. This x plus y still equals 180 for an isosceles trapezoid where all those things are congruent. So yes, opposite this is that. That means I can make some sort of circle that circumscribes it. Where? Oh, sure, about maybe like this. Not even close, really. Yeah, there's some circle that can circumscribe an isosceles trapezoid in any way, assuming that this shape is what this thing made, and I believe it did. So maybe it looks a little bit like that. There. Right? So there's the one that's circumscribing that. Cool. Anyway, there's the reason. All right. Let's change pages. So number 29, modeling with mathematics. 3 moons. I thought I said 3 moms. 3 moons. A, B, and C are in the same circular orbit 100,000 kilometers above the surface of a planet. The planet is 20,000 kilometers in diameter and measure of angle ABC is 90 degrees. Draw a diagram of the situation. How far is moon A from moon C? So I have a planet. I have a planet here. That was about its center. This diameter, and let's go horizontal across, makes it a little easier. This diameter here is 20,000 kilometers. They mentioned 3 moons are in the same circular orbit 100,000 kilometers above the surface of the planet. So here's the planet itself, and here's something that there's a different orbit like this one. Maybe not drawn to scale. But they said 100,000 kilometers above the surface. So if the surface is here, here's an additional 100,000 like that. Which means from here to here, that's 100,000 plus 20, that's a diameter on this guy here. So half of that's the radius. So if I wanted to get another length, and I don't know if this is used or not, but if I wanted to get this here, this is going to be 100,000 plus 10,000, because the diameter is 20,000, so half that's the radius. So 110,000 if that's used. I don't really know what's used yet. Let's take a look. The planet is 20,000, and measure of angle ABC is 90 degrees. What are they? Oh, the moon stuff. So what I want to do, let's actually get rid of that other one. I don't know if that's going to be needed yet or not. Let's kind of draw a full diameter out like that, and let's find some. Here's some moon here. The way for it to be 90 degrees, guys, is for one of these to be on diameter. So yeah, let's just keep it in green. So A and C can be 2 moons right here. B can be anywhere here, and this is going to be 90 degrees, period. The measure of this angle of moons A, B, and C is 90, so as long as 2 are on the diameter, this is a 90-degree angle, boom, like that. So there's a 90-degree measure. What's the question? Draw a diagram. How far is moon A from moon C? Oh, that's the part I was kind of answering before. So how far are they from each other? What's the diameter of that whole thing? If this is 100,000 there, this is 100,000 here. I mean, we could speak more in other terms, but I just got to add 2 of these 100,000s plus this 20,000 like that. So the length of AC, this isn't a measure of an arc, it's that length. We're going to take 2 of the 100,000s, that's 200,000, plus the 20,000 here, which is 220,000 kilometers. That's the distance from A to C. And there's the diagram. Number 30. At the movie theater, you want to choose a seat that has the best viewing angle, always. So you can be close to the screen and still see the whole screen. Oh, now it sounds like an IMAX screen. See the whole screen without moving your eyes. Oh, I see what they're saying. You previously decided that seat F7 has the best viewing angle, but this time you someone's sitting there. Where else can you sit so your seat is the same viewing angle as F7? Explain. So we saw an example of this, like it was like a Statue of Liberty example from before in the notes. But this is the similar kind of esque thing. What you want to do is if F7 basically wants to be somewhere on a circle. You want the movie screen to represent a diameter of your circle. So notice where I'm kind of putting my mouse right here. I'm going to extend this outward like this. And notice this circle. And I'm going to place the edge of the circle on F7. Whoops, that's not the diameter. Is this drawn to scale? I guess, well, that's not really drawn to scale then, right? I want F7. This isn't really drawn to scale. But what you would want to imagine, let me put it on F7 and pretend like the movie screen goes outward like this, more so. And then, because that would have, boom, like that right there. Did they? No, I take it back. Maybe it's not like that. I thought they wanted a right angle. Okay, let me do that again. What I want to do, I'm trying to think how I want to draw this circle then. Okay. There's a center that exists. Not to my knowledge where. There's a center that exists for this such circle. I got to kind of fake it till I make it. Let's pretend it's kind of like that. I thought they said a right angle, so I apologize. But F7 basically represents an inscribed angle where there's a chord made from the endpoints of this thing right here. Boom and boom with this intercepted arc. We just need to make sure that we have another seat that's on that circle that has the same intercepted arc because it would have the same exact viewing angle for us. So what I could do, I'm trying to find a good color, maybe yellow. What I want to do is, like, this would be a good seat right here. This D3, if you will. That has the same angle. That's the same angle as that F7 seat. So is this one right, let's say right here. Maybe you don't really love that thing, but as long as it has the same viewing angle, it's good. So where else can you sit? Anywhere on an imaginary circle whose inscribed angles include F7 and any other seats that have an intercepted arc spanning the width of the movie screen. So examples could be like kind of that D3, if you will. And what's that one? B8, 9, 10, 11, 12. B12, something like that. Maybe. Just because I did that one to scale. You probably wouldn't write that, but I'm just filling that out as an example. Okay. Let me get some sniffles out of the way. All right, here we go. Let's go to number 31 in writing. Okay, a right triangle is inscribed in a circle and the radius of the circle is given. Explain how to find the length of the hypotenuse. So this is something where I feel better about seeing how they represented the theorem. I'm sure I could have went, well, if you do this. The only way a right triangle is possible to be inscribed in a circle is if, we're talking about an inscribed angle whose intercepted arc is a semicircle. So if we go across a diameter like this, the only kind of right triangles that can exist is a point on the circle, boom, like that, and we're talking about an inscribed angle like so. So in this case here, this is a right angle, this is a right triangle, and the diameter is the hypotenuse. So when they're stating, how do you use the radius to find the length of the hypotenuse? The radius is half the diameter's length, and the hypotenuse is a diameter of the circle. Therefore, the radius is half the length of the hypotenuse. So how do you find it? You double it. So you double. That's how you find it. All right. There's 31. Number 32. How do you see it? Let point Y represent your location on the soccer field below. What type of angle is AYB if you stand anywhere on the circle except at point A or point B? They don't ask to explain, but that's just going to be a 90-degree angle. What type of angle? It's a right angle. Angle AYB is a right angle. Now the reason, I'm not going to write it out, but this is kind of what we were mentioning above. That's a circle down there. And AB represents the diameter of that circle. So any point that's not on there like that is an inscribed angle with an intercepted arc that's a semicircle, all that kind of stuff. That's a 90-degree angle. Any of those ones for that angle. So this could be that Y that they're referring to. Always 90 degrees, a right angle. Very short, how do you see it? Let's go to number 33. Explain why the diagonals of a rectangle inscribed in a circle are diameters of the circle. Oh, of a rectangle inside there. All right, so if I have a circle, and I'll make up a rectangle inside of there. So let's go like, boom. Okay, that's the way that'll hit. You have to keep in mind that rectangles can always be inscribed inside a certain circle of some sort, and rectangles always have 90-degree angles. The 90 plus 90 is 180. That seems to pan out. 90 plus 90 is 180. But because these are right angles, then therefore, where these chord things go, or excuse me, where the ends of the angles go, that will represent a diameter going across like that, and that's also the diagonal of the circle. Because an inscribed angle with 90 degrees has an intercepted arc that is the semicircle. So that will always happen. So I don't want to explain that in kind of a rough sounding way, so let's just try. A rectangle will have only 90-degree angles, which means when inscribed in a circle, it features inscribed angles of 90-degree measures. And their intercepted arcs, and their angles, their angle endpoints, their endpoints, I'll just say, are on the diameter, are on a diameter of the circle, which would also represent the diagonals of the rectangle. So hopefully that kind of pans out for you. It does for me, at least. All right, number 34, thought-provoking. The figure shows a circle that is circumscribed about triangle ABC. Is it possible to circumscribe a circle about any triangle? Justify your answer. Yes. Now, I don't know the justification that I want to state. I'm sure there are ones that have a lot more to do with what we're doing, but any 3 points, let me type it. 34. Any 3 non-collinear points make a triangle, and any 3 non-collinear points make a circle. Therefore. So yes, any 3 non-collinear points make a triangle, and any 3 non-collinear points can make a circle. So there's one version of it. Here's another version that I guess I'm going to state that works itself out. This makes more sense with the stuff. Alternatively, the measures, the interior angle sum of a triangle is always 180 degrees. So, to inscribe a triangle to inscribe a triangle inside a circle means for their intercepted arc sum to be double their measures, their angle measure sum, which would always be 360. That's probably the one that they wanted, because you probably don't know the other part of that makes it true, and maybe that's why the top part is true to begin with. Okay, number 35. In fact, it looks like we're doing a lot of proofs moving outward. So as great as this was for a while, now that we're past that hour mark, this could stretch out a whole another hour in and of itself, depending on what we have to do. You can see number 35 as parts A, B, and C. On number 35, we're going to prove the inscribed angle theorem with 3 different cases. If an angle is inscribed in circle Q, the center Q can be on a side of the inscribed angle, inside the inscribed angle, or outside the inscribed angle. Here's the center that's on it. Here is a center that's inside of it. Here's a center that's outside of it, assuming that this is the angle we're talking about right there, the ABC. ABC, ABC, ABC. Prove each case of the measure of an inscribed angle theorem. This is the one that I'm most familiar with when it's on it. So given the angle ABC is inscribed in circle Q, let measure of angle B equal x degrees. Center Q lies on BC. Prove measure of angle ABC is half of measure of arc AC. So here's the angle that we're talking about. Here's the arc we're talking about. We need to prove that that's half of that. All right. So they say show that AQB is isosceles, then write measure of arc AC in terms of x. So to prove that this thing's isosceles is going to be very straightforward, or to mention, Q is the center. So Q to any point on the circle will represent a radius, which means these two things will be congruent to each other. If they're congruent to each other, then it's an isosceles triangle. So in this case here, we have AQ is equal to BQ because radii of a circle are congruent. So if they're congruent, it's an isosceles triangle. Therefore, triangle AQB is isosceles. Now, if it's isosceles, that means that you also have other angle measures that can work itself out, such as this x guy right here. If this is x degrees, this is x degrees right there. If both of those are x degrees, you might remember, you might know from old cases that this triangle has an exterior angle here. What's called the exterior angle theorem of a triangle is the sum of the two remote interior angles is equal to the sum of those is equal to the measure of this one here. So if those are both x's, x plus x will be 2x degrees. This is, again, the exterior angle theorem. So the measure of angle AQC is going to be x plus x. That part says to me 2x degrees, like that. And that's a central angle. That's a central angle. And a central angle is equal to the measure of its intercepted arc. Therefore, the measure of arc AC is also 2x degrees. Now, 2x degrees means double the original bit, so that seems to work itself out. That's part A. So what we did was we showed this thing's isosceles, used something to find out what the measure of this external one was, and there are different ways you can kind of make that happen. Again, this is the exterior angle theorem. I always call it the remote exterior angle theorem. I'm trying my hardest to not say that, but exterior angle theorem's right there. And then with that theorem in mind, we now have a central angle. A central angle is equal to the measure of its intercepted arc. Part B, case 2. Use the diagram and auxiliary line. So this BD is an auxiliary line there to write given and prove statements for case 2. Then write a proof. Wow. Okay. I don't even know where to start with that one if I have to do the given. What, given auxiliary line BD? Is that what they want to say? Or inscribed angle, such and such? Let's do given. How about, well, it's not just an auxiliary line, right? It's a diameter. But let's start with the fact that there we have an inscribed angle. Angle ABC is inscribed in, what is it? Circle Q. In circle Q. We're also given that DB, segment DB is a diameter. So we want to prove that the measure of one thing is half the measure of the arc thing, right? So we want to prove the measure of angle ABC. ABC is half that of the measure of that intercepted arc that we're talking about before, right? So that's measure of arc AC there. Okay, so we can use the previous case to work off of this. I feel like that's a pretty good jump that we can mention, because if this is case 2, case 1 can be used. So if we already found out that this AC is some 2x, then that means that this guy here would be x degrees like that. I think that's somewhat of a start that we can work off of. Well, it's a different kind of x though, right? So maybe we can't say that necessarily. But, so listen. We showed the inscribed angle thing right here, right? But now what we can do is use these two different inscribed angles and show that these are halves of these parts. So half of this is that guy, and half of this is that guy right there. Okay, not congruent to each other, but at least that part's there. So if we want to prove that the whole thing is half of that, we can use the arc addition postulate. The reason why we can do this here is because the last one had a diameter. The last one had a diameter. Now that we have this one as a diameter, we can work that out. So I can say that the measure of angle ABD is half the measure of arc AD. That's using case 1 because there's a diameter there. And let's do the measure of angle DBC is half the measure of arc DC, also from case 1. Now we get to use the arc addition postulate and the angle addition postulate, things like that. So we can say this: the measure of angle ABC is the measure of angle ABD plus the measure of angle DBC. That's the angle addition postulate. Now, the arc addition postulate says that the measure of arc AC is equal to the measure of arc AD plus the measure of arc DC. That's the arc addition postulate. Therefore, and I'm not going to kind of say by transitivity and what have you, but this, if this is half of those, should I just say halves here? Half of this is half of that plus half of that. Does that kind of work out too? I mean, it does, but is that okay that I can use that there? Maybe not yet. Let's just apply halves in like green, saying this was an afterthought. We divide everything by 2, take half of those, and boom. So half of this plus half of that from this plus that means that we can say that the measure of angle ABC is half of the measure of arc AC. Because measure of angle ABD is half of this guy, measure of angle DBC is half of that guy. When you add them together, you do get that total, which is also that. All right, so that's case 2. Now, part C, case 3, says use the diagram and auxiliary line to write this one. I guess the same thing can be involved, but it's through subtraction. Now we're going to take something out. So let's see if I can kind of work that. Let me kind of copy and paste this and see how well I can call this a subtraction problem and just be good from there, because it's still the arc addition postulate and the angle addition postulate, but just kind of in a different way. So it's still the given, and that's still a diameter, right? Yeah, we're still showing that it's that, but in a different case. So instead we can do a subtraction of what we have. So we have this angle, or we're proving that this is half of that. That's a lot of things that are written. I got to change the spacing. This is still ABD. ABD, this guy here, is still half of that whole. And ABC is still half of that whole there. So there's no change in what we do, with the exception that there is subtraction between these things. Measure of angle ABC, it's ABD minus ABC. Yes, minus DBC, excuse me. Minus DBC right here. And arc AC is this minus that. Honestly, it's the same thing except just a subtraction. Now we take AD. We're going to take all of AD and subtract CD, or DC as I put it, and then you get that AC like that. Still divide them by 2, and you still get that part. So that copy-paste job, I think, is just going to be very easy to mention there, and we're all good. So it got a little faster at the end, which is good. That's why I said I'm only really familiar with that first proof. It's nice to know that we can kind of use those things afterward. It doesn't have to be in the diameter, but it does apply there. All right, number 36. We're going to write a paragraph proof of the inscribed angles of a circle theorem. First, draw a diagram, then write given and prove statements. So I talked about this one in the other in the lecture portion. Inscribed angles of a circle. Oh, this is the one where they all share the same. This is the one where they share all the same thing. Is that what they're kind of talking about? Yeah, it's the one where you have multiple. I thought this was the inscribed polygons. I misthought. What are we talking about? So let's say we have, these guys right here, and then these guys right here. See, the main idea again when we do this. Notice how I did draw it. Let's color code them. These both represent angles. That represents an angle with that intercepted arc. This represents another angle with that intercepted arc. But they share this intercepted arc right here. And I got to give these things letters clearly. Let's give it A, B, C, D. Great. Okay. So what we want to do is say, given that we have two inscribed angles, right? Given this is an inscribed angle, this inscribed angle, but they intercept the same arc. So given angle, let's call them BAC and BDC, they are inscribed angles. Inscribed angles intercepting arc BD. They intercept arc BD. Okay? What we want to do is prove that they're congruent to each other. So prove that, and this is going to be a quick one as far as the transitivity property, the transitive property I should say, prove that angle BAC is congruent to angle BDC. So we know the inscribed angle theorem and the idea of these things here. So we have measure of arc BD. We have measure of arc BD equaling half the measure, the measure of the inscribed angle is half the measure of the arc. So measure of angle BA, oh, I call this BAC. It needs to be BAD. Let me do this again. BAD, BAD. Then I totally messed this up. BAD, and this is BCD. Okay, I'm sorry how I wrote this thing out. I was looking at something different. So BCD. BAD, BCD. Okay, let's do that again. All right, the measure of angle BAD will be half the measure of arc BD, because that's how inscribed angles work. And the measure of angle BCD will be half the measure of arc BD as well. Once again, they share the same intercepted arc. By the transitive property of equality, we can say that the measure of angle BAD equals the measure of angle BCD. I know I'm not doing a full two-column proof thing on that, but this is the inscribed angle theorem. I think that's what it's called, inscribed angle theorem, and the transitive property of equality. By the definition of congruence, these two will be congruent. Like so. Okay, I think that works out. So, if that's the case, we can move forward. Let's get number 37. The inscribed right triangle theorem is written as a conditional statement and its converse. Write a plan for proof for each statement. Oh boy. What? Conditional statement and its converse. So write a plan for proof. I just want to write what the statements are. So in number 37, so remember, the original conditional is if you have, I think, a right triangle, then the hypotenuse is the diameter. So what we want to say is to prove the conditional, to prove the original, we're going to find the measure of the intersected arc of the right angle. Now that will be double the measure of 90 of the right angle. And the definition of a semicircle. So that's the whole thing, right? The semicircle. To show the hypotenuse. See, we're not proving, we're doing plan for proof. To show the hypotenuse of the right triangle must be the diameter of the circle. Second, let me take care of a sniffle. Man, just when you think you're out, they reel you back in. I'm seeing a slow-mo thing back and forth on here. I think they're trying to see if someone got hit by a pitch. So that's the plan for the original proof there. See, the whole idea is when you have this right triangle concept, that 90-degree angle has an intercepted arc that should be double the 90 degrees. It should be 180. Well, semicircle is also 180 degrees. So you're trying to show that those things match. And if they match, that means the endpoints of the right angle must be on something that makes a semicircle. Therefore, those endpoints must also represent endpoints of a diameter. So that's the plan for proof there. It looks like we're not actually proving that one. Now, they also mentioned the converse. So the converse would state, to prove the converse, let's see. To prove the converse, let's see what we say there. The converse states that if you have a diameter, then the angle, yeah, it was the same thing. If you have a diameter, then that inscribed angle is a right angle, that it is a right triangle with that intercepted arc. So use the definition. So now we're going to start with the definition. Use the definition of a semicircle and to find the measure of the angle opposite the diameter. To find the... See, this time you just go straight into that inscribed angle bit. You just take half the measure and it'll be 90 degrees. And if it's 90 degrees, then it's a right angle. Then you have a right triangle. So that's the plan for proof. We don't actually prove itself, it seems. And there it is. All right, 3 more questions. We have another proof, and it's the last proof before some critical thinking. Copy and complete the paragraph proof for one part of this guy here. Okay, cool. We just get to fill in blanks. Now, I mentioned this answer before. This is the one I thought we were talking about here. So I mentioned this answer before. The idea, which is pretty cool, is that any two opposite angles, their endpoints form arcs which complete the entirety of your circle. And that equals 360. And because inscribed angles are half that, then that sum will be 180. If you didn't understand that, we'll do it again. Given a circle C with inscribed quadrilateral D, E, F, G, measure of angle D plus measure of angle F is 180. Oh, we have to prove that D plus F is 180 and E plus G is 180 there. Not congruent, supplementary. By the arc addition postulate, measure of arc EFG, boom, plus measure of arc, we can say EDG is 360 degrees. So boom, boom, boom. This plus this should be 360 as a whole. Now, they also do the same thing with FGD right here and DEF, also 360. I probably want to say GDE then. GDE. It seems like they want to kind of go in a full circle instead of opposite ways. GED. Wait, hold on. First they said EFG, now it's GDE. Using the blank theorem, measure of arc EDG is double that of the measure of angle F. So is that called the inscribed angle theorem? Is that what we're going to be working off with that? Because the basic thing is normally we talk about it being half the measure of the intercepted arc. Now we're mentioning that the intercepted arc is double. So I'll say inscribed angle theorem. I'm not sure if I'm supposed to be able to fit this inside here or if we're just supposed to write it separately somewhere. So if it's double that measure, so EDG, boom, is double F. EFG is double D, and DEF is double G, and FGD is double E. By the substitution property of equality, two measure D's plus 2 measure F's should be 360. Those are the ones that are opposite each other. So, if you divide everything by 180 by 2, then you get measure of angle D plus measure of angle F is 180. Similarly, we can do the same thing for the others. We can say measure of angle, what was it? E plus G. Measure of angle E plus measure of angle G also equals 180. Okay. Yeah, you're dividing everything by 2 when you show that the full things add to 360 from those opposite angles. The intercepted arcs opposite those opposite angles. All right, 2 more questions. We have number 39 on critical thinking. In the diagram, angle C is a right angle. If you draw the smallest possible circle through C, tangent to AB, the circle will intersect AC at J and BC at K. Find the exact length of JK. C is a right angle. If you draw the smallest possible circle through C, tangent to AB, through C, tangent to AB. I guess they mean in such a way that it's hitting, I think they just mean this kind of thing here, something we've been doing a lot of, kind of like that. They say tangent to AB, it means it only hits AB once? Oh, tangent, oh. They're talking about like this, I think. Boom, like that. Okay? I believe. The circle will intersect AC at J and BC at K. Is that what they want? Find the exact length of J. Is that what they meant? Or did they mean... I don't know if they mean that because that doesn't really look like something that we're... Maybe. Because now we have... Maybe. Because now we have a little diameter here because that's still a right angle. So maybe that's what we get to work off of. I can't really tell if that's what they're actually saying, though. Sure, let's go off that. When they said tangent to AB, I'm going to go with that. Okay, so find the exact length of JK. Let me think about how that thing would work itself out when it comes to like distance outside of here. That's a right triangle. This is like a diameter. If that's a diameter, this thing's tangent here as well, by the way. I'm trying to think if that will have any use. We have the 3 and the 4 and the 5. Obviously, those will be of use for us. So 3, but 3's the whole thing. That's where I kind of am at a loss myself thinking what to do. Let me think about what I want to do with this one before I keep going. Hold on. All right, in a quick thought, here's the best I could come up with. I think it should work. Let me move this, re-enlarge it, and kind of talk through it. So in this one, I think I'm going about it this way. I don't think my drawing was big enough to really work it out. So I think doing this will help me feel out what I want to do. When I draw this circle thing through here, tangent to AB and through circle C and stuff, I was trying to decide whether, first of all, this part would be parallel. The answer is no, it wouldn't. So the thing I'm talking about is this J and this K, right? From J to K, that's not parallel to the AB. Not even close. At least this drawing looks a little bit better, though. So JK. Here's the thing. I don't need to really look for this, at least. I don't think that's the thought, because I don't know what portion of these things would apply. But here's the thing. We do know that this is a diameter. This is a diameter. What I'm curious about, and I think it does work, is that this altitude straight down should hit that tangentially because this needs to be a right angle like that. And if that's a right angle, then this works as an altitude from C down to there. The question is, should that be down there on the bottom of that? Yes, because this is the smallest circle from C. That means this is the topmost that this can go and the lowermost that this can go. This is important because if these two are congruent to each other, then I don't need to look at this one, but I need to look at this one. So from J to K is going to be this distance as well. I can call that X. Now I don't really need the circle anymore. I don't need the circle. I just need to look at this. That's what I think we got to do with it. If this is our setup, then I think we can solve because we've done this right triangle stuff before. So what I can represent as X, X can represent, for example, the short side of this medium triangle. This is something I did in the previous chapter. The short side of the big triangle here is 3. So short of medium divided by short of big, I can do hypotenuse of medium 4 divided by hypotenuse of big 5. And that can be a proportion set up to solve for this thing. That's the way I'm going to go about it. I think that makes most sense with regard to what they wanted to set up. We still mentioned diameter from the beginning, so it does apply to this section. Cross multiply and you get 5x equals 12. Divide both sides by 5, you get x equals 12 fifths. 12 fifths, hold on. Excuse me. The exact length is 2.4. I don't know if we want one or the other there. 12 fifths or 2.4. And that's where I'm going to go with that one, number 39. Looks good to me. So JK is also going to therefore be, say, 2.4. I think they'd like to see a decimal there. Now remember what the original drawing looks like and where that JK would actually be. All right, last question, number 40. There are 2 parts. Let me sip water and read it. You are making... Now here's the thing. It's quite interesting that I thought they were going to do more on inscribed angles, and these are inscribed angles, but they're really, really hitting hard that part in the semicircle stuff, the right angle stuff. You're making a circular cutting board. To begin, you glue 8 1-inch boards together. Okay, right here. I guess 1-inch width. As shown, then you draw and cut a circle with an 8-inch diameter from the boards. Okay, that all makes sense with what we have. Part A. Segment FH is a diameter of the circle cutting board. Okay, that must mean that this is a right angle here. They might ask that. Write a proportion. Oh, this sounds a lot like 39 suddenly because we have the altitude thing. So this will be a right angle. Write a proportion relating GJ, and JH. State a theorem to justify your answer. Oh, I don't remember the name of the theorems. I mean, it's similar triangles and stuff, and we have angle, but I don't know if they mean geometric mean and that kind of stuff. I don't think I'm going to be able to answer that specific thing. But GJ, and JH, if I say relating it, if I say GJ to JH, this could be a lot of what I just did from the previous problem. GJ can be the short side of the medium triangle. Oh, JH is right here. JH can be the short side of the small triangle. So short side of medium over short side of small. Now let's get another two things in medium and small that can correspond. It can really be any two things that you want as long as it goes from medium to small. I can do hypotenuse of medium, which is GF, hypotenuse of small GH. I can do FJ, the long side of the medium, and GJ again, the long side of the small. I think I have multiple options here. If I want to use, say, GJ twice, then I could do that one. That way we can probably talk about the geometric mean theorem thing that we have. So this is short side of medium over short side of small equals. We can do long side of medium like this over long side of small. Now I have GJ multiple times, and JH is also there. I think that if we use that one, then the theorem we can refer to is that geometric mean theorem. This was out of section 9.3. So I think that would just work itself out like that. That's the setup. Part B, find FJ, JH. Oh, perfect. FJ is part of this. JH and GH. What is the length of the cutting board seam labeled GK? Oh, I forgot. Yeah, these are actually, there's an actual length here. So this length is 8. That length's 8. Do they kind of have other lengths? Can we do other ones? Or the angle things we should do? If this diameter, is there another chord radius? Find FJ, JH, and GJ. What is the length of the cutting board seam labeled GK? Oh, we have other parts right there that we can mention. Interesting. So they said 1 inch cutting things cut into these. Oh, if these are each 1 inch, yeah. So, okay, that whole thing's 8. That would mean that this guy here is 2, and this guy here is 6. The 2 and the 6 make the 8. So I guess we can use relations that we wanted to before. Is there anything else we can do? Absolutely. I would say just find that GJ. I'll call it X right now. Find that GJ based on what we have here. And I think that's how we can do the relation. So GJ, this unknown, X over JH. I have 2. That's long, short side of medium, short side of small. Now we'll do long side of medium 6 FJ over long side of small. This GH is unknown X. So I'll get X squared equals 12, and X is the square root of 12, or X is 2 root 3. So there is an answer for GJ right there. So this guy's 2 root 3. 2 root 3. Not 13, but 3. What is the length of the cutting board seam labeled GK? GK, I guess, should be 2 of those because this is a diameter. This is perpendicular. Oh, yeah, exactly. Yes, it should. So, I mean, I already knew that it should, but we can talk about the theorem. So, from G to K, if I can erase all this stuff for a moment, I hope that's all right. I want to copy and paste this over. I can undo that if you'd like me to. But I just want to get this guy over here, and then I want to kind of draw on it. So let's undo what I did there. Okay, awesome. Okay, so G to J, and this is the last part of the last question we have to do, is 2 root 3. G to K, we're going to double that. Now, how come? This is a diameter. I think they said it's a diameter, what have you, as such. A diameter intersects a chord. When it intersects it perpendicularly, it bisects the chord. So if this is 2 root 3, then this is 2 root 3. Now, those are exact values. So the length of G to K is going to be 2 times 2 root 3, which is 4 root 3. Is this inches? Inches, like that. Let's see what that calculator approximation is. 4 times 3 square root is 6.9, around 6.9 inches. So that's how that thing works with the diameter. That's the length of the cutting seam board there. All right, guys. And that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I know that it obviously went slower as we moved along. A lot of things with proofs there, but I hope a lot of that made sense. Stay tuned for section 10.5 whenever that one hits. Take care. I will see you in the next one.